2026 supplement for the Calculus BC course, and if you're doing the AB course, I believe this is from lesson 4.4. Okay, those of you in the AB course, I think the diagram actually is different, so maybe you can cross out your diagram and draw this one here. Also, I think I left out something, so let me just add this little extra bit F, and let me make this line straight, a nice horizontal line, and now we can actually go about doing this question. So it says, let's consider a function f of x that's continuous over a closed interval. Let's go from a to f now, not a to b, and differentiable at every point on the open interval from a to f. Okay, continuous and differentiable. Nice. So here's the graph of the function. I'd like us to complete the following table. So if I talk about increasing, the graph is increasing. What intervals of the x values show that the graph is increasing? You might be thinking, oh, from a to b. Very good. I'm going to use interval notation. So from a to b. Anywhere else? Anywhere else? You could say also from d to e. Perfect. I'm going to use the union symbol to join the two intervals. So it's either this one or that one. That's where the function is increasing. Now, what is the formal definition of increasing? If I were to compare two x values in the interval, okay, one of them is less than the other, so don't write this down, but just watch. If I said this is x1, this is x2, of course we have a corresponding value of y, f of x1, and we have the corresponding value of y here, f of x sub 2. And for an interval to be increasing, what we should see is, yes, that the f of x sub 2 is always bigger than f of x sub 1. Good. Now, this is calculus. That formal definition was probably from pre-calculus. We're talking about slope now. Slope. What do we notice about the slopes of all the points in the interval from a to b and d to e? If you're thinking, slope, 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 I'm looking at tangent line slope, 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 slope. They seem to be all positive. Very good. So therefore, our slope definition here is that the derivative must be bigger than 0, or it has to be positive. Good. Can you now do the same thing for decreasing here? Which interval is it decreasing? Yep, from b to d. Notice in this case now, if I were to compare an x1 with an x sub 2 and the corresponding y values, yes, this time f of x sub 1 tends to be bigger than f of x sub 2. And then, of course, ultimately here, I'm looking at this idea of calculus, I'm looking at slopes. Slopes in these seem to be, you got it, negative. So everywhere where it's decreasing, the slope is negative. Okay, how about constant? Yes, this is why I had to add in the extra little interval, right? Yep, from e to f, definitely. Notice in this case, though, that the y values at x sub 1 actually equal the y value at x sub 2. And if I asked you for the slope of the tangent at all of these points, well done. You would say the slope equals to 0. So, as a summary here, if I ask you to figure out if an interval is increasing or decreasing, there's actually a test. If the derivative is bigger than 0 on the interval, then you know the function is increasing on that interval. And if the derivative is less than 0, then you know that the function is decreasing on that interval. So how can we actually tell then if a critical number, which we call c, remember this is the x value, is a maximum or a minimum? Well, all we need to do is just look at what happens to the derivative just to the left and just to the right of that critical number. Look up here again. Where are our critical numbers? Right there. Right there. So if you think about it, what happens to the left of this maximum? Notice that the slope is positive, and what happens to the right? It is negative. So for the point x equal to b, the slope to the left of it is positive, and to the right of it is negative. And the conclusion here is then, therefore, you get a maximum. And then for x equals to d, slope before is negative, slope afterwards is positive, and there you get a minimum. So therefore the slope to the left of it is negative, and to the right of it is positive. In this scenario, you get a relative minimum. So if you're looking at the slopes just to the left and to the right, how do you tell if it's a local max or local min? Well, I'm just going to summarize what I just said. We're going to call this now the first derivative test. So the first derivative test says a local max occurs if the derivative changes from positive to negative at the critical number. And similarly, a local min then. Once again, it's about changing derivative. Ooh, how come I have purple? F prime x changes from negative to the left to positive, and then once again at the critical number. And then the question is, what happens if there is no change in the derivative? Like the slope is both positive to the left and the right, or negative to the left and the right, then yeah, there is no max or min. Okay, so that, my friends, is the first derivative test. So now let's use that first derivative test. Yes, please turn the page. And let's see if we can actually do some of these questions together. So now I don't have a graph, but I've given you an analytical function here. F of x equals x cubed minus 3x squared minus 45x plus 1. I'd like you to find the intervals where the graph is increasing and decreasing, and then determine the values of c that give the function a max or min. Okay, so how do we figure this out? Increasing, decreasing? Yes, it's about the slope. And if it's about the slope, I need to find the derivative. So let's quickly calculate the derivative here. Derivative of x cubed, of course, is 3x squared. Derivative of 3x squared is 6x. Derivative of 45x is 45, and derivative of 1, of course, is 0. And really need to find the critical numbers first, so I'm going to set the derivative equal to 0 to find the critical numbers, CNs. I'm actually going to factor out a 3 as well, because I see that all those terms have a factor of 3. Beautiful. And then I can use my lovely factoring, two numbers that multiply to negative 15 and add to negative 2. Yes, negative 5, positive 3. We can then make this equal to 0. We get x equal to 5 and x equals to negative 3. Nice. However, this is where the critical numbers occur. That's where we have a relative max or min, but we don't know which one it is, and we also don't know if it's increasing or decreasing on the intervals. So what we need to do is our next step is to actually make a derivative number line. And I want you to then test each region to see if the slope, right, the derivative of the slope is going to be positive or negative. So let me draw my number line here. This is my f prime number line. I'm going to label it as f prime. I'm going to plot my values, negative 3 and 5. Now can you see how I've split my number line into 3 separate sections now? So ultimately here, what I want us to do is to actually go ahead and figure out what the value of the derivative is in each of these sections. So for the one in yellow, perhaps I want to actually test out, let's say, a number like -4. And if I plug that into my derivative, right, because it's the derivative number line, I think, let's see, 3 times 16, 48, plus 24, minus 45. It's big, isn't it? It's big. It's going to be some positive number, right? So therefore, this region here must be positive. The whole region must be positive, okay? If I were to take a number between -3 and 5, yes, take the easiest one, 0. Plug it in, I get -45. I know then this region must be negative, right? And then finally, if I plug in f prime of 6 or something like that, what do I get? I guess I could have plugged it into this one. Maybe it's easier plugging it into here, actually. That's just 3 times. What is that? 6 plus 6 times. Yeah, I think it's, yeah, so what is that? 6 plus 3 is 9, 9 times 3 is 27. This is just 27, right? Positive as well. Okay, so we've got our number line. So what? Well, using our number line now, we can analyze and get our answer. So where is the function increasing? Increasing means where it is positive. So notice it's from negative infinity all the way to -3, and also from 5 to infinity. And we'll take the union together. Okay? Where is it then decreasing? Well, that's when the derivative, of course, is negative. So in the interval from -3 to 5. Now, can we use this first derivative test now to figure out where it's a max or min? Yes, a max occurs when it goes from positive to negative. So I'll say c equals to -3 is a local max. I'm going to ask us to give a reason, because f prime changes from positive to negative. Okay, and how about the other critical number? Well, if you said that must be a local min, you are correct. Can you tell me why? I know you can tell me why. Because it changes from negative to the left to positive on the right. There you have it. Done. Okay. So I'd like you to do the same thing for example number 2. Same pretty much question here. Just a more funky function. And I'd like you to try and practice figuring out the derivative of that yourself using the product rule. Hint, hint, hint. And then come back and check your answer with me. Okay, this is a nasty, tricky one, so if you want to just check from time to time, then of course pause the video, watch a little bit, then pause again, and just check bits at a time. All right, go ahead, press pause. Remember, a and b. A prime, which is 1, b, which is 1 minus x to the power 2/5, plus b prime. Ooh, I see. Chain rule. Don't forget the -1, right? The hook-on factor from the 1 minus x. That's b prime, and then a. Right? So that part is chain rule. Cool. Now, not so cool is trying to make this equal to 0, but I'm going to actually ask you to factor something out. Can you see how both of these have a factor of 1 minus 2x, but we're going to factor out the lowest power, in this case 1 minus x to the -3/5. If I do that now, taking this term divided by 1 minus x to the power 3/5, the base is 1 minus x, so we're going to subtract the exponents because we're dividing. So on the side here, 2/5 minus negative 3/5 just equals to 5/5, which is 1. So we have an extra 1 minus x to the power of 1. I'm not going to put that power of 1 there because it looks like a derivative. I'm just going to say 1 minus x. Okay? And then factoring out from the second term here, I see a 2/5 of an x. And actually it should be minus 2/5 because of that negative 1. I almost forgot. And so once again, what I did here was, oops, what is that? What I did here was I just factored the greatest common factor. Okay? This helps because remember, I want the derivative to be equal to 0. So when I solve, I just have to make this part equal to 0. 1 minus 7 over 5x equal to 0. So therefore, negative 7 over 5x equals to negative 1. X equals to 5 over 7. Bravo. Okay? That's when I make the first derivative equal 0. You might be thinking, I might this equals 0 too. Well, remember, this is a negative exponent, so that's 1 over 1 minus x to the positive 3/5. And I can't really make that equal 0 because it's 1 divided by something. But remember, critical numbers occur when the derivative equals to 0 or when the derivative, that's right, does not exist. So I actually can make 1 minus x equal to 0 because that's a point where it does not exist. So x equals to 1. Not a critical number, but a place, or sorry, yeah, it is a critical number, but it might not be a max or min. How come? Well, I don't know. We'll find out soon. It could be. We'll see. So, once again, how do we figure out if it's a max or a min? Well, we have to go and make our, that's right, number line f prime. Plot 5/7 and also plot 1. Okay. Here you go. You have to test out the regions. I will not test them out for you because I'm tired. But I hope you did it yourself. And if you didn't, shame on you. Press pause and work on it now. But if you did it, I hope you got positive here. I hope you got negative here. And I hope you got positive there. So therefore the maximum occurs at x equals to 5/7, while the local min occurs at x equal to 1. So even though, right, that was where it doesn't exist, it's still a critical number. And what you'll see from the number line is that, yes, it does become a minimum. Because to the left of it is slope is negative, and to the right of it, the slope is positive. All right, that's all.